Hello, my name is Laura Alford, and this lecture is on the intact stability of submarines. Now, when I talked about intact stability before with the surface ships, I started off talking about static equilibrium, and I want to do the same thing again with submarines because submarines are tricky. All right, static equilibrium. Two conditions, right? Sum of the forces is equal to 0, which means that the sum of the buoyant force has to equal the weight of the submarine. Is all. And then for condition 2, the sum of the moments has to equal to 0. Now for surface ships, this is it. These are the two conditions that you're looking at. But for submarines, you have to meet these two conditions, but while the submarine is at the surface, while it's diving and surfacing, and when it's at depth. So immediately, your job just got 3 times more complicated. Yay! All right, so here's an illustration. Same submarine. Condition 1 is when it's at the surface, condition 2 is that it's diving or surfacing, and then condition 3 is when it's down at depth. For this one here, the sum of the forces is equal to 0 in all 3 cases. The weight is equal to the buoyant force. But in each of these 3 cases, the numbers, if you will, wouldn't be the same. So it wouldn't be the same weight or the same buoyant force, but they are in equal measure in each of these 3 cases. All right, so condition 1 is met. For condition 2 now, this is when we bring in the center of gravity and the center of buoyancy, right? So the weight acts down through the center of gravity and buoyant force acts up through the center of buoyancy. All right. If condition 2 is met, then the centers are aligned vertically and there is no moment, right? And you'll notice here that when the submarine's at the surface, that the center of gravity is above the center of buoyancy, but in the other 2 cases, for how I've got them here, the center of buoyancy is actually switched and it's now above the center of gravity. That doesn't mean that it's necessarily unstable or anything, that's just where they are. But I just want to point that out. I didn't mess it up. All right. If the centers are not aligned vertically, then the moments are not summed to be 0, so there is going to be some sort of moments here. All right, the moment will try and bring those centers back to be aligned vertically, so that again it's in static equilibrium. Okay. For the case where there's 0 heel, right? This again goes back to when we're talking about the surface ships. There's the center line of the submarine, and then K is the intersection of the keel and the center line with the baseline there. So okay. Again, this is going to assume port and starboard symmetry with the submarine. Okay. So as I talked about before with the surface ships, it is not enough to have your submarine be in static equilibrium. We also have to know whether or not it is stable. In this case, we're going to talk about intact stability. So in general, stability is just what happens when the ship or the submarine is tipped over, right? And we have transverse stability and we have longitudinal stability. So this, just a real quick review. Hopefully remember the metacenter, right? And it might have been a while since you saw those other videos, so do a quick review. The metacenter is that imaginary point that the ship rotates around if you heel it over. Right, so the center buoyancy swings over a little bit, but the ship is sort of rotating around this indivisible point called M, transverse metacenter. Right. Point of M is that if you can get M from getting BM, which is the metacentric radius, you can then get GM, which is the metacentric height. Right? And you get GM by using this stuff. Right. So if you calculate KB and BM from your hydrostatics program, you can get KG, you then calculate GM. Right. GM is important because that is going to be our measure for our initial transverse stability, right? So if you remember this picture here where we take the ship and we tilted it over a little bit, put where the center of buoyancy has shifted over to, drew GZ, added in the arrows through which the buoyancy is acting and the weight is acting, and then we say, okay, GZ is the riding arm, right? And then the weight of the ship times GZ is the riding moment. It's actually what's going to cause the ship to go back upright. But if we know the weight, then we need GZ, and we can approximate GZ using GM times sine of phi, which is the heel angle. This holds for the small heel angles. Right, so again, going back to GM is the measure for our initial transverse stability. We take that, we do the same thing with the submarines, okay? Because it's all fine and good if you're operating the surface, but if you're a submarine, you got to do it this way, right? You got at the surface during diving or surfacing or at the depth. And the procedure is the same. You tilt the submarine over and you draw the arrows and you calculate GZ by estimating GZ using GM times the sine of phi. But you can see that because of the different cases, you've got different GMs that are around, different GZs, and so you can't design the submarine just to be operating at the depth or just during diving or surfacing or just at the surface. It has to be designed such that in each of these cases you're going to have a safe GM value. All right. One side note, when you are at depth, you need to keep the center of gravity down low. Here's what I'm talking about. You'll notice here that the metacenter and the center of buoyancy are actually at the same point when the submarine is at depth. So what it means is that the submarine rather, is going to rotate about its center of buoyancy. Right. So here we go. The submarine on the left has a center of gravity that's below the center of buoyancy. So we tip it over, draw the arrows. The submarine on the right-hand side has a center of gravity that's up high above the center of buoyancy. We draw the arrows, we get a moment, and in this case, as you can see, on the left-hand side, because the center of gravity is down low, it's going to cause the submarine to come back upright. But on the right-hand side, because that center of gravity is high, it's going to cause the submarine to flip over. And so a center of gravity that is low gives you a stable submarine. Center of gravity that's high gives you an unstable submarine. So keep the center of gravity low. All right, to illustrate how these values are changing, especially with GM, as the submarine goes from the surface down through diving and into fully submerged, I put together a few slides here. So in the beginning, right, this is at the surface, you've got center of buoyancy, center of gravity, the ballast tanks are nearly empty, all right. If you remember from that's the effects of loading on stability lecture, we talked about the free surface effect. The free surface effect is when you have liquid that's sloshing around in a tank, that will cause a virtual rise in the center of gravity, and we called that G double prime, so that's marked down here. Because the ballast tanks are nearly empty, that virtual change in the center of gravity is not very much, so it's just a little bit above G. Now, you get the call to dive, and so you start filling ballast tanks. You fill the ballast tanks, the submarine starts to sink lower into the water. This is causing B to rise, but G to drop because you're adding water into the ballast tanks. Then G double prime is tracking along with G. But then as you get closer to this midpoint here, you've got now B and G are going to cross, right? Because we know they have to cross at some point, because we know that the center of buoyancy is going to end up above the center of gravity. So there's some point where they coincide. Right in here, the ballast tanks are partially full, which means that you've got a lot of free surface effect going on. So you see the bigger difference between the virtual center of gravity G double prime and the actual center of gravity G. See, with the change in the underwater geometry, M has dropped. Now B is starting to track upwards. G and G double prime are down low. Now we're coming closer and closer to being at depth here. And then finally here we are at operating depth. M and B coincide. You've got G and G double prime are now below the center of buoyancy. The ballast tanks are now nearly full, which means that we've got a reduced free surface effect again. So the G double prime and G are closer together now. So this just sort of shows that this is very complicated, right? And you can see how dangerous it can be during diving and surfacing with all of these values changing so rapidly. So designing the submarine with hydrostatics, you have to be very careful to keep all this stuff in mind. For stability at large angles, there's something very unique that happens with the submarines. So the geometry really determines the change in the center of buoyancy, right? So take a look at this. We've got the ship on the left-hand side and a submarine at depth on the right-hand side. As the ship heels over, right, the center of buoyancy really changes quite a bit because the underwater geometry of the ship is changing so radically. But for the submarine, the whole thing's underwater already. And so the center of buoyancy doesn't change, it's in the same spot. GZ, then, it depends on the relative locations, right, of G and B. And in the submarine's case, G is actually just going to essentially go around in a circle. And picture it in your head, right? I don't have a good way to do a video, but just picture the submarine continuing to rotate, and G's just going to track out a circle. And that's reflected in the actual GZ curves for a regular surface ship and for a submarine at depth. For a ship, you've got the GZ where it starts out low, and there's some maximum GZ, 45 degrees, 40 degrees, something like that. And then rapidly as water comes over the deck, and then eventually the ship will capsize. But for a submarine, because G is just traveling, it really looks like a sine curve. And so the maximum GZ for a submarine when it's at depth is actually at 90 degrees. So it's very different than a surface ship. With this GZ comparison, I really wanted to add two lines for the submarine when it's at the surface and the submarine when it's diving or surfacing. But it turns out that those GZ curves are highly dependent on the ballast tanks that you have, their size and their location. And so there wasn't really a good generic one that I could put up there. So rather than confuse the matter, I will just say that the GZ curve depends on your ballast tanks and where they are and how big they are. We'll leave it at that. All right. So to wrap up, the two main concerns stability with submarines are these. When they're at the surface, submarines generally have poor surface stability just because they don't have that much waterplane area. So the stability at the surface has got to do with how much waterplane area that your ship or your submarine has. And just due to the nature, then they just don't have that much. So that's the trade-off, right? I mean, submarines primarily are designed to operate well under the water. So their stability when they're at depth is great, but it's less when it's at the surface. So you just have to keep it in mind and watch out for it. And then the second thing is, again, going back to the free surface effect that we've talked about before. When we talked about in that other lecture, where we said, okay, free surface effect, very bad. What we'll do is for transverse stability, we'll make it so that instead of having wide tanks, we'll have long, narrow tanks. And that way there won't be as much sloshing and there'll be lower free surface effects and we will have a stable ship. Excellent. That becomes a problem when you're a submarine and you are actively diving and surfacing and you have long ballast tanks and that water gets sloshing around and you have high free surface effects. So that there's ways around that. You can put baffles in the tanks and try and control some of that sloshing. But again, it's another tricky thing about submarines that a lot of the typical things that you do with a surface ship can't be translated directly to a submarine because it has different design constraints. So anyway, I hope this was a good sort of just general little introduction to hydrostatics on submarines. I had a lot of fun making this one. It was very educational for me as well. As always, thanks for watching and have a good day.